Valence bond theory. The goals in this podcast is going to be first to sort of set up the idea between valence bond theory and molecular orbital theory so that you get a little bit of an idea of what we're going to be talking about for the next few videos and classes. So after this, I want you to be able to recognize and identify the shape of a sigma bond, pi bond, and multiple pi bonds. We won't be able to finish all of this with this video. We'll have to talk about hybridization, but you should be able to kind of get a feel for the shapes of these and a general feel for what they look like. So first of all, some introduction. We have two different types of theories to work with when we're talking about bonding, and we pick and choose these based on the application. So the first is valence bond theory, and this is going to encompass hybridization, which we'll talk about in a different video. And in valence bond theory, each atom is going to retain its own orbitals. Now, these own orbitals are going to overlap with each other, and these atomic orbitals, the orbitals that the atom itself has, form the bonds. This is going to be very different from molecular orbital theory, where instead what we're going to do is we're going to take the atomic orbitals, we'll take those wave functions that we learned about a while ago, combine them, and then make molecular orbitals out of them. So first, let's go a little bit more in depth into what a bond actually is and how we're actually forming these. So what's the concept of what's happening here? So to form a bond, we've already talked about bond lengths, and we know that there's a certain bond length for certain bonds, right? So why does that happen? This graph shows us why that happens. In order to have a bond, you have to have these orbitals overlap. So here we have this one of the simplest examples, hydrogen, H2, and if we start them out way far apart from each other, there's no bond here. So it's a long internuclear distance. They're a long ways away from each other. They're not at a bond. And so that's over here in the graph at just a zero potential energy. So this is a non-bonded. Now as you start moving them closer and closer, these orbitals are able to overlap a little bit. And this stabilizes things because now each hydrogen is able to kind of share a little bit of its electrons. It's getting closer to each other. These electrons are in the center, so the nuclei aren't repelling each other, and the energy starts to go down. And then as you get closer and closer, you reach this low point, and this low point is your stable bond. And so here we have this with the s orbitals overlapping. Those s orbitals overlap to form what we're going to call a sigma bond here in a minute. And that forms your stable bond and your low point on the energy graph. Now, I don't have it drawn here, but you see this skyrockets up if you get any closer. So think about what would happen if you kept trying to move these closer and closer. Your nuclei would start repelling each other. And so that's what's going on here. The nuclei repel each other. So this is your most stable bond. All right, now let's talk about how to recognize types of bonds. So here I'm going to go with sigma and pi bonds, and that's what we're talking about. Now, I have a sort of structure of a molecule drawn out with some pictures. This little picture will make more and more sense as we go along in the videos. We don't know quite enough to explain it all right now. So we're looking at the general shapes at the moment, just the general shapes. So if we look at all of our sigma bonds, I've labeled them all for you. The sigma bond, sigma bond, sigma bond. Those are coming from all of these atomic orbitals, which is what I have drawn in, overlapping with each other. And what I mean by cylindrically symmetrical is you're going down the axis of a cylinder. So if you draw a line across from one nucleus to the other, you get a line of symmetry from here to here, and from here to here, and from here to here, going along the bond. Now, how do you know when these are sigma bonds? Well, your first bond, your single bond, is always going to be a sigma bond. You have that as your starting point. That's where, like in our skeletal structures, we would draw that first bond going through. And then once all of the things are interconnected with each other via sigma bonds, then you can start adding in your next sort of bond, your pi bond, if you have double and triple bonds. So something to mention about these bonds are going to be freely rotatable. You can rotate along sigma bonds. And that's just because there's nothing to stop it, there's nothing to lock it. You just have this collection of electron density that's able to move around. Pi bonds are a bit different. So with pi bonds, you have a different situation if you have one pi bond or if you have two. So I mentioned on the sigma bond section that our sigma bonds are our first bond. So in a situation right here we actually have a double bond. we have a sigma bond going here to here. That builds our skeletal structure that connects everything. And then our second bond, or the thing that makes our double bond, is formed from the p orbitals. So again, we're looking at general pictures. You don't quite have enough information to see exactly how this works. So we're just kind of looking at the shapes and getting a feel for them. So look at this pink double bond, or the second bond, our pink pi bond. Notice some things about it. First of all, going down the center, there's this what we call a nodal plane. The top and the bottom are symmetrical to each other. We could fold them over on top of each other. Also notice there are two lobes. So we have a lobe here and we have a lobe here. So pi bonds, that first, if you only have one pi bond, so you have a sigma bond and a pi bond, that's going to have two lobes and you're going to have this plane running down the center. Now, what this plane does too, or what this two-lobed system does here, is it locks it into position. You can't rotate that, because in order to rotate it, you'd have to break this lobe and break that lobe and then reconnect it. And so double bonds, they don't rotate. They're locked into a position. Now this changes if we have a 2 pi bond system. So that would mean that we have to have our sigma bond as our starting point, and then we add 2 more bonds to it. So that's our triple bond. So if we have a triple bond, and I'll show you a picture of this later. This example doesn't have one on it. It's also going to be cylindrically symmetrical and freely rotatable. And we'll see that it kind of ends up doing like a hot dog bun style thing around it. And so we'll see why that works here in a minute. So let's kind of look at just how each one of these are made. So sigma bonds can come in a few different ways. The first one being, like, let's say you have 2 s orbitals. So here I have your 2 s orbitals. And they overlap. There's no real end to this, so they just overlap. They're a sphere. That is one way of forming a sigma bond, because you can see that it's cylindrically symmetrical. It's symmetrical across this, and so that's one way of forming a sigma bond. Another one would be if you have a p orbital and an s orbital, and you allow those to come in contact with each other. So here we have our p orbital and our s orbital, and they start apart and they come in, and you get along this line a cylindrically symmetrical bond. Now the last way, you could have 2 p orbitals. And now with the 2 p orbitals, there's something very important about this. Look at how they're connecting to each other. They're end on end. It's the 2 ends coming together. If you were to overlap them side on side, that would be something very different. So these are all of the ways of forming your sigma bonds. Now, something I haven't mentioned yet, and I'm going to put it in very briefly here just because it's important to note, we haven't learned about hybrid orbitals yet. Hybrid orbitals can do all the same things that I showed you here, where they can overlap end on end, and that will also form sigma bonds. So put a little note down, even if it doesn't make a lot of sense right now, that says hybrid orbitals also form sigma bonds. So those are your 3 different ways of forming sigma bonds. Notice in each case, I've had them all here so you can see them together, you have this cylindrically symmetrical system where along the bond, they're symmetrical. Okay, now let's go back to this picture one more time so you can see everything again. So same slide as before. So now let's look at this one more time. So here we have our s orbitals, and they're actually hybrid orbitals. We'll show you what exactly those come from next video. So we have our hybrid orbitals and our s orbitals overlapping end to end, just like you saw the p orbital and the s orbital doing. They'll act the exact same way. And here you have the 2 orbitals overlapping end on end, so it's a sigma bond. 2 orbitals overlapping end on end, so it's a sigma bond. Now let me show you what the pi bond is, though. Because right here, you have here and here, you have your 2 lobes, that's your pi bond. And so think about what your p orbitals would look like coming up and down, and how those p orbitals would overlap. So now we'll look at this one more time, starting from the Lewis structure. So I've been using this as sort of an illustrative example. It's good to go back now that we have all of that example set up and start from scratch. So here I have CH2, CH, CH3. So if I wanted to, let's draw the Lewis structure, and then we'll also draw the line structure. So I can draw the C, with the H's, and then our last C. And if you were to draw it just like that, what you should notice here is not everything has an octet. And so we look over here, and each of these carbons only have 3 bonds. So we need to add in a double bond. You should by now have a little bit of a feel for how these organic structures work. And so it may not be 100% necessary for you to count up all the electrons and work through it. If you're not sure though, just start back from scratch. Start back from counting the electrons, setting up your skeletal structure, and working your way through everything. Now, let's also draw the line structure for this, just because I want you to have some practice with that. So we have 3 carbons. So I put my pencil down. 1, 2, 3. And I have a double bond here. So that's my line structure. Okay, so now if we look at this and we compare the two, we can see here we have our CH3 group, here we have our CH bonded to this, and here we have our CH2, and we have our pi bond. All right, here we have C2H2. So we'll start by drawing in our carbons. Now we have our 2 hydrogens, so we'll spread those out evenly. If you didn't know to do that, you can start with putting them on both carbon, and you'll see that you won't be able to make it work. So here we have this. We have 4 more electrons left over. If you add up all of your electrons, 4 from each carbon, 1 from each hydrogen, we have 4 left. So there's no way to make an octet out of this except if you give it a triple bond. Now, since I said the first bond, the single bond, is always going to be a sigma bond, that means that the other 2 are going to be pi bonds. So what happens here is we have our carbon here, and then those are attached to our hydrogens. And then the p orbitals that are coming off from the carbons, they form something very similar to what we saw in the pi bonds before, but now they can just wrap all around, and they form this sort of hot dog bun style or corn dog style setup. So you get your carbon here, your hydrogen, and then the p orbitals from the the p orbitals from the carbons form this cylindrically symmetrical cloud of electrons. Okay, so what you should have taken away from this video, and keep in mind there's actually some pretty advanced concepts hidden in this video that we'll go over in a later video. But I just want you to have a general idea of the difference between valence bond theory and molecular orbital theory. And then be able to recognize the shape of the sigma bonds and the pi bonds. You don't necessarily know exactly how those are formed yet, especially because we're involving hybrid orbitals, which we'll talk about next video. But just recognize the shape. Recognize these sort of cylindrically symmetrical, where they're end-on-end shapes, or where they're S's overlapping with S's. Or if those p orbitals are overlapping side to side, keep that in mind, as that's what makes your pi bonds. And that's what you should get out of this video. Just recognize what these look like, have a feel for what this bonding really looks like, as opposed to just drawing a line on a piece of paper.